It's my great pleasure to introduce our next speaker, Professor Russ Tedrake. Russ is a professor at MIT, as well as the VP of Robotics Research at the Toyota Research Institute. He has had a number of impactful works on learning and planning for various robotics problems, such as locomotion and manipulation. Many of his papers have won or been nominated for Best Paper Awards in top conferences, including RSS, Coral, ICRA, CVPR, etc. I am always deeply impressed and inspired by these works from Russ Lab in terms of their solid program formulations and amazing experiment designs grounded in real-world challenges. And I personally really love his recent works on key point representations and shape representations, which bring novel insights to utilizing visual perception for robotic manipulation. Very excited about his talk. And Russ just shared a presentation live in the chat box. So if you want to ask questions, you can also use this link. So let's welcome Russ.
Thank you very much. Yeah, the link is also at the top of this, and I've sprinkled it a few times in the talk in case people miss it. You know, so I'm a hardware roboticist, experimental roboticist. We work hard on beautiful robot videos, and it pains me to think that you might watch them at a low frame rate. So if you click here, then you get to watch it in your browser, and it'll download directly to your browser. You'll get the full experience. But so thank you for inviting me, and thank you, Sonia, for that great talk. I think that actually we have very complementary talks here. So I also am very interested. This is really a talk about state representation for manipulation, and in particular, some of these questions that she brought up at the end about how do you generalize across object classes are exactly the kind of problems that we really want to address here. But as I've maybe given people a minute to open up those slides, I have to warn you, so I'm a dynamics and controls person first. I've come to perception much more recently. If there's any other dynamics and controls people out there, I have to warn you, if you get queasy, this next slide might make you a little queasy, okay? And what I want you to do on this slide is think about what is the state of this system? Okay, what is the state of this system? Now, I'm used to walking robots that have, you know, a handful of links and whatever, but my gosh, thinking about the hybrid mechanics of contact and you know, this is just blowing my mind as a control theorist, okay? And this is really the kind of task that I want. It shouldn't be out of scope to do something basic in the kitchen, and humans have no problems with this. But somehow all of the math I've been working on for the last how many years kind of falls down if we were to try to do this problem, okay? So, so what kind of state representations do we need to do problems like this? And I'm not going to get all the way back to onions today, although we have some work on that will be presented at Wafer. But I want to start talking about the problem, at least at this sort of sweet spot we found, which is the same one Sonia identified, of trying to manipulate at least classes of objects. Let's keep them rigid for now to start, although we'll show you some non-rigid things. But I'd like to at least have a representation to start that would work equally well for all of these, you know, all of the objects across a class. That already breaks my thinking as a control theorist in some sense. So you know, but it turns out there's a couple of pretty simple ideas that go a pretty long way in terms of working with the, you know, scaling to this level of task. So one of those is this idea of key point affordances. And that's worked with Lucas and Wei will give a follow-up of this as one of the spotlight presentations this afternoon, and Pete. Okay, so the idea here again is to do something where you're given an entire category of possible objects, shoes in this case, and you'd like to do something that involves some level of precise manipulation. It's not just pick it up and drop it in the bin, but somehow it matters that the toe goes forward on that rack and the heel goes in the back. And we'd like to be able to even talk about what does it mean to define a geometric task on a category of objects. Okay, so here's the basic problem statement. We'd like to manipulate potentially unknown, but we'll keep it for rigid to start with, objects from a category, mugs and shoes will be some favorite examples that we use, into a desired target configurations to be defined in terms of our new state representation here. Okay. And now the straw man is to just try to define the pose in 6 degrees of freedom, 7 numbers, let's say, pose, it's for the objects. That seems like that's what we tend to do if we're manipulating known objects with CAD models. But it turns out you don't have to think too long to realize that it's actually very hard to come up with a canonical pose over a rich category of objects, a whole rich class of objects. So even the notion of what is the heel, what is the toe, these things, these things are consistent, but the notion of where is the center, or what is up, can vary widely, especially if there are kinematic constraints on those things. Okay, so if you take away my crutch of thinking about the sort of state in the Lagrangian sense of what the system is, then how do we even specify the task? How do I write down a cost function so I can optimize it? Do I just have to work with images of mugs on the rack? Is that, do I go all the way from problems I know and love to full image complexity? Okay, so it turns out, of course, that there's this great idea about key points, using key points. It came out of the computer vision literature, and it turns out that this is, in our view, sort of the minimal semantic information that you could give. It's addressing a similar problem to what Sonia was just talking about, but in a more minimal sense. Like, if I really want to just put the mug on the rack, I could define that with a single point instead of identifying the entire region. So it's maybe a simplification in that sense. I could point with a single point to say what's the bottom of the mug, and a single point I could say what is the opening of the mug. And it turns out if I'm reasoning about the geometry of those key points and the transforms that they'll undergo if I start manipulating them, then that actually turns out to be a pretty rich semantics for describing the tasks that we want to do. So it's kind of a simple idea that goes a pretty long way. And of course, key points work very well in practice. So you have to play to your strengths in that sense. This observation came at the time where we had just finished the DARPA Robotics Challenge, and we had built up a pretty strong library for inverse kinematics, thinking of it always as an optimization. We were dragging Atlas around by its hands, but also programming tasks for Atlas's hand, saying, like, for instance, you want the palm of your wrist to be normal to the entire surface you're about to grab. And there's this rich library of sort of geometric constraints that you can put together. If you're walking, you want to make sure that your feet stay underneath your center of mass and things like that. But it turns out, as soon as we started thinking about key points, we realized that could fit just right into the basic inverse kinematics formulations we've been working with, right? But key points alone are not a sufficient representation. So Sonia, for instance, was labeling the entire segmented point cloud with the semantics. And this is different by just having a few key points labeled semantically. We still need to do something online with the dense geometry. So it's kind of separating those two concerns. So for us, we can define the kinematic transform that we want the points to undergo. But in order to grab the object and start moving it along that transform, we're going to take a quick snapshot of the instantaneous point cloud, or we can use a dense reconstruction mechanism in order to sort of accomplish that entire manipulation task. So the key points are not a complete state representation, but they can be used sort of with the local sensing to give enough to do the tasks, so do a wide variety of tasks. I also really liked Sonia's experimental results, and we similarly try to do a lot of things on the real robot and run, statistically significant tests and the like. So this is just a sampling of the types of different tasks that we had tried. We trained on 10 different objects, tried 20 different objects of the same class. This was the shoes on the rack numbers. We placed it on the shelf 97% of the time, and with some accuracy numbers on the heels and the toes. Wei has done many things to continue this work. One of them, an early one, was to add shape completion into the mix, so that you could, because one of the pain points before was if you don't understand the occluded object, the occluded parts of the geometry, then it was impossible to write a constraint in the configuration space of don't run into things with the bottom of the mug, for instance. But putting a shape completion network to task, off-the-shelf shape completion, added that capability, and it was a very nice addition. And we will talk about how far you can go sort of with dynamics, and actually surprisingly with these kind of representations in his spotlight. Okay, so that's the initial idea. And then in that case, key points are really, they're geometric, of course, there's points in space, but we've also made them a semantic label for parts of the object. So the mug handle, the front toe of the shoe, these are the semantics, of course, of that object. And in order to provide that, we required human labels, and we made an annotation tool that made that fast and easy, but still it was the human adding the semantics, okay? If there's tasks where we don't need those semantics, and we just care about the geometry, maybe we can take the human out of the loop completely. And there's a bunch of good stuff that was happening about using dense reconstruction to train these things. So the question is, can we put that to task and get rid of the human labeling? And that was this idea, we've been using this idea called dense object nets, which was also Pete and Lucas's work. In fact, all of this today will have Pete and Lucas's pictures on it. And the core technology then to push that into the self-supervision range is this idea of dense correspondences, which came out of Tanner Schmidt and Richard Newcomb and Dieter Fox's work. We just applied it to objects and showed that robots could self-supervise in order to do this, and made some small changes. But this animation that you're seeing here, on the left is a single point that's we're mousing over just to say this is the point of interest, for instance. In the center, you're seeing the heat map of the possible correspondences that the network has learned of saying, what are the points on this new image, unseen image, that correspond to the same point in the original image. And then you see the full RGB image on the right. So that is it's a presentation format that I hope that made sense, because we're going to use it a bunch in the next few slides. But again, the point on the left is like a point of interest we're trying to see, and we're humans, let's say, mousing over just to highlight it. And then on the right is the corresponding objects learned by our network. Okay, and again, the way that we obtain those is the robot does some self-supervision by doing dense reconstruction first, 3D dense reconstruction. And then for every image that it's taken around the object, it has a photo along with the dense reconstruction. So it can basically say this pixel and this pixel were the same, and these pixels were different. And you give a pixel-wise contrastive loss, and suddenly you can start training a self-supervised network. Since the time that they published the initial paper on that, they've done a lot of work to make those, to trying different loss functions to sharpen the performance and the like. So on the left is the mouse over. In the top center is the heat map using the method at the time of the original paper, and now you can see our correspondences on the bottom are a lot sharper than they were before. So that it's just a better training procedure, and you can, if your eyes are good, you can see the point of highest correspondence labeled on the right. The other thing that we've done is sort of in practice, it became useful to do it instead of a single robot, single camera on the wrist flying around the robot. We would train these things now with multi-camera multi-view, and give them 3D, project them down into 3D. So we have 3D correspondences trained more efficiently. The amazing thing that sort of came out almost by accident to begin with was that we get these class consistent descriptors just by that training method. If you train one hat at a time and all independently, and there's no reason for the network to label them the same or label them differently, it tends that they learn the same representations, the same descriptors. It learns correspondences across object labels. And that's something we've continued to try to investigate and understand, and merits more work, I think. You can also train them by throwing multiple hats in at the same time during the training. You can train them to distinguish those. So it's a surprisingly cool instance versus class capability of those networks. Okay, so the question is, so those dense descriptors, you could think of them as self-supervised key points. They're extremely dense representation, lots of points, so maybe not the key points, but they're certainly points that are consistently pulled out, and it's beautiful that they're self-supervised. But if we don't have that semantics, then how do we specify the task, right? At the original time, we could already have a simple interface, which is that we'll just click once on the image, we'll do the correspondence, we'll use the local point cloud, and we can do a pick, basically a context-aware pick. And that was a good start, but we want more than that, right? So it turns out, we wanted to go even to more dynamic tasks for sure. So the next paper I'll talk about here a little bit is the dense object nets applied to visual motor imitation learning, okay? So, I mean, basically the imitations are providing the task that we had trouble specifying without the semantics, okay? So to set this up, we looked at a lot of the good work on visual motor policies, and these things, when you watch them it's very compelling that they're using feedback in a way that most of our robots aren't. They aren't stop, plan, you know, sense and then plan and then move and making big mistakes. They're making very reactive, based on the camera's input, motions. And so we look more carefully at how those systems were being architected. And there's a big feature that emerged, which is that actually people normally have a very big perception network, which is this O image going in that maps a relatively small set of features into the feature vector Z. And then we pass in, for instance, the robot's configuration also. And then a relatively small network that actually is doing the policy for this. And there's a bunch of ways people have trained that, pre-trained that image network, for instance. A lot of times people used, like some of the three sort of canonical ways to do that would be if you had the notion of pose in your system, then you could use a pose-based auxiliary loss to try to train those initial features. People have used autoencoders to train those features, and people have even tried to train that network end-to-end, successfully train that network end-to-end. And we're going to compare against all three of those. But what the proposal here is today is a little bit different, right? We're going to use the dense descriptors as the front end. So we're going to take our image in, push it into the dense descriptor network, come out with first a dense image of correspondences, but actually, in order to turn that into now a sparse representation that we could push into a small policy, we're going to choose sort of our 5, 10, whatever D favorite descriptors by just identifying vectors in the descriptor space and applying the correspondence function. So we're going to find the D points as close as with the highest correspondences to our canonical points on the hat, for instance. And we're going to pass those in as our key points now, self-supervised key points, directly into a smaller policy. Okay, so we did this first with imitation learning. Simulation was a super valuable tool. We did a lot of the vetting and everything in simulation on hand-coded policies, just trying to copy our original hand-designed controller into this visual motor policy. And also we did teleop to simulate the real robot. Pete got very good at, with his mouse keyboard to do all kinds of cool things with the KUKA. And honestly, it blew my mind on how well these things worked. It really changed my impression of what the representations we should be working with look like. This was actually a small policy. This was an LSTM, and the history did appear to matter, but only about 100 LSTMs. And for pushing boxes and flipping boxes in simulation, it worked surprisingly well. But what really got me was how well it worked in reality. So for pretty non-trivial tasks, including deformable objects and the like, this not only could it accomplish the task, but it had that feel of robustness. Let me show you a couple of my favorite examples here. So this is just grabbing a plate, okay? This is sort of the basic example that was teleoped. The dense descriptors are pre-trained not on this particular, we separate the dense descriptor training from the actual imitation learning. But that gave us a robust enough representation with those correspondences to find the key points that once we did a handful of imitations, we could apply it in a variety of visual scenes and get surprisingly impressive robustness. You can see all the different things that it's experiencing here that were absolutely not in the imitation data, and it just worked incredibly well. And again, the magic there is that we're tracking these correspondences online and then pushing that into a small policy. And the evaluations we did on this were to compare the dense descriptor-based features with the other features that I showed you in the prior art. And there's a lot of, this is small enough that all I'm saying is that there is data, and I hope you look at the paper if you care about it. The takeaway message here is that it's still imitation learning, and it has all the limitations of imitation learning. So the networks tended to perform very well, the dense descriptor networks in particular on the right. The basic takeaway message was there's kind of a convex hull of examples that we seem to have given it. And if you're in the convex hull of things that's seen before in the imitations, then you're gonna like your performance in reality. But this is still very narrow and very fragile. If you change the task a little bit, or you go outside your envelope of training, then you're gonna have to go and imitate some more. So the last piece I'll just mention quickly really here is trying to take the last step with that idea and see if we can do the same thing, but with a lot less demonstrations and with more generalization. And so now the most recent results are on dense object nets for model-based control. And this is, late breaking results. Like I think the video came in last night, but Lucas is back in the lab and doing the last few experiments. He's had the technology ready, but he needed to get back in the lab to do the last few experiments. And now we're taking the dense descriptor key points, learning a forward dynamics model, another network, to basically learn the forward model in the key point dynamics space, okay? And then now we have a deep network model, forward dynamics model, and can we do trajectory-based planning through that model? And I'll just show that again. So this is sort of what it looks like. It's done in a model predictive control with then a receding horizon when you get to the end. You specify the target in terms of key points at the end. In this case, in this example, he's actually giving a single demonstration to see the optimization and give it targets along the way. And then it's planning how to control that box in order to get it there. And it does pretty non-trivial things in terms of stabilization and in terms of, it gives the same look of robust performance, but this time you give me a new task, you give me the new task in the form of a single demonstration, and there's no extra demonstrations required. So Lucas is finishing this up lickety split, and he's giving his defense next Monday. And so you should check it out either live if you send Lucas a nice email, he'll give you the Zoom link, or you could watch on YouTube right after, but he's going to give a great defense next Monday. Okay, so what I continue to want is state representations in general, but certainly to start, I'm already happy with trying to do dexterous things with a category of nearly rigid objects, or where the deformability of the objects didn't impede the complexity of the task too much. And this is what I've tried to present here. So we have key points as a very simple representation of the category level geometry, but we combine it with local sensing and dense reconstruction in order to get the full representation we need. And now we're trying to say if it's more than geometry, if we can actually write the dynamics, how far we get with dynamics. I mean, the rough takeaway is that the dynamics prediction works very well in a variety of tasks. But honestly, once you've got a model in the form of a deep neural network, planning in that model is still hard, maybe harder than people fully admit. For task specification, we talked a little bit about annotated key points, human labeled key points with semantics. That gives the semantics of the task. That's a beautiful way to describe the task. But with the self-supervised description, we just use demonstrations to say what we want. Now, I don't want to give the impression that we think key points are everything. We absolutely don't. This is a good tool. It makes a lot of things that felt hard feel easier, but they are certainly not the state representation of to end all state representations. Pete likes to say that they won't tell you when the eggs are done cooking. That's maybe the extreme case, but there's even some more similar cases than we've got right now that where key points are not enough. One of the examples I really like, if you think about what's the right state representation for tying your shoes, it doesn't seem like it should be that hard of a problem. But if you start thinking about it, a human looks at this and has a pretty good sense of some discrete state of like, is there a loop? Is there a knot? How far am I in this rope tying? But boy, how do I get that out of a continuous model of my deformable rope? I'm not sure. Okay, I'll end with that. I do want to say though that I will be teaching my manipulation class at MIT online. I'm trying hard. Partly this slides.com is an experiment with how to make these things work well online. And for those of you that were nice enough to download them right now, you'll see that it's loading a little renderer. And this is, anybody who's got this on their screen can interact with the robot. And we're going to try to put our complete manipulation stack basically so you can run it on Colab and have all the tools that we are able to offer in any mature sense, and try to teach a class with it. So that will be online, YouTube and everything like that. And I hope you come.
Thank you for the great talk, Russ. And it's fantastic to see how Russ connect to other talks in this workshop and connect the dots. And I have a question. So in several of your recent works, you proposed object category level kind of like representations for objects. I wonder, going beyond, is it worth, to also take into consideration of, for example, the agent's capabilities and mechanics or the task semantics to these visual representations?
So I guess the bigger view I have in my head is that we should be equipping our robots with skills. Skills are feedback controllers. They work for some things. They don't work for other things. In state space, it's easy. You have some set of states where you can stabilize it. In these problems, I don't know how hard it is. So the question is, how much should one policy, one skill try to accomplish? And I think the category of objects feels like sort of the level where we should expect one controller to work over a lot of spoons or a lot of mugs or a lot of shoes. And then we had a task and motion planning workshop yesterday that was actually a lot of fun. Then you have to build up a whole repertoire of those capabilities for different categories of objects. And that's where I think you start completing. And by the way, Sonia also talked at the task level more than we've addressed with any of this work here. But I think that is the next kind of step, is to bring those local representations, local skills, and compose them into bigger systems.
And we got a number of questions, so I don't know how long we can keep Russ with us here. But since the next session is lunch break, I guess we can take just a few more. Yeah, cool. So one question from Konstantinos. Is it possible that the key points become occluded when a grasp is performed?
So we frequently have occlusions. You can train the key points either to only recognize the occluded key points or the unoccluded, the visible key points, or you can train them to recognize, because of our dense reconstruction, we can actually train them to hallucinate the key points that are actually occluded. And we've done both. In some tasks, it makes sense to do both. So for instance, we have a key point on the bottom of the mug, and we want to set the mug down with the key point, with that key point on the ground. So that is working absolutely right through occlusions. I think that's one of the strengths of the key point approach. It's a good question.
The next question from Georgia. Isn't the key point method completely bounded to having models of these objects?
We don't have any models anywhere in anything I said. Right, our only models are in the sense of we scanned the objects with our robot right before we started manipulating them. So there's never been a CAD model in that pipeline that I talked about today.
The next question from Gao Tang. With so many learning components involved, how is trajectory optimization done, especially in the MPC case? Does local optimizers such as SNOPT work as usual?
Oh, good question. So yeah, I think it's kind of weird, right? That everybody talks about learning deep forward models, and then they say you can do planning, and we're going to just do cross entropy methods, because cross entropy methods is not a particularly good way to do planning. Some people have done more work on there, but my impression at this point is that more work is needed. That you're not done if you have a deep network that predicts your model. I think control design and planning is still hard there. So I don't think you give it to SNOPT and you get the answers you like. I think that's a great question.
And also an anonymous attendee asked on the high level, what is the advantage of control compared with learning for robotics manipulation? That's a big question.
That's a big question, but I love it. I think, let's see. Well, I think generally what's happening in the field due to learning is all amazingly good. It's forcing us to ask more aggressive questions. It's challenging our notion of state and of representation and all these other things. But I would say compared to most people, maybe I'm more optimistic that actually the controls community can rise to the challenge and give us controllers. I don't think you should have probability 1 guarantees, but I think if you think about robust control, for instance, as a way to regularize your controllers to be robust against lighting variations and object geometry shapes, I actually think there's a lot more work to do. I sort of, I would like to see and help try to drag robust control up to the level of manipulation, because I think it has a lot to give.
The next one from Anirudh. How do you plan using these key points without having a forward model of how the key points would move when the object is subjected to an action? For example, how do you plan the path of the shoe? He said, maybe I didn't understand the setup correctly.
No, it's good. It's complicated because there was multiple pieces of the story, and Greg has a question after this, I think. In the first case, where the KPAM, where it was the human supervised very sparse key points, we just said, we're gonna assume that they're approximately rigid. We're gonna grasp the object anywhere and expect now that the key points will then, after we've grasped, maintain a fixed transformation with my end effector. Therefore, if I move my end effector, I understand the transformation that my key points are gonna undergo. In the imitation learning, it's much more subtle. The answer is somewhere buried in the layers of that network. But the idea is that is still sort of the information that you would need to accomplish the task.
So Greg, go ahead.
I think it was a great talk, by the way, of course. So my question is, it's a little hard to answer because it talks about speculating about biology, which I think is generally kind of dangerous and potentially misleading. But my sense is that for manipulation tasks and things related to that, our ability to create some meaningful semantic structures is not so great. Whereas for vision tasks, it's really quite good. And so do you think the reason is because vision is somehow related to speech and communication? So it's intrinsic, it's like we've evolved just to make that better? Or is there something intrinsic about manipulation that makes partitioning, you can't really make good options. Like there's lots of stuff where you'd like to have the right vocabulary in the manipulation world, and we just don't have it as people.
I think we have a bunch. If I had to, I remember I had a good conversation with this before, but let's say I was on vacation and my swim trunks had this problem. I got them out of the luggage and the cord was like, didn't go all the way to the hole, right? I just communicated something pretty weird about dynamics and manipulation to you. Okay, now the way I resolved this was actually I scooted the swimsuit along and I pinched with my fingers and I moved it along and I moved it along and eventually the cable came out and boom, right?
So you can describe the process, but the semantics of the individual steps, like tying your shoe, right? We don't really have that. Whereas, I can talk about the buttons, the shadow, every little thing in the visual world has a name.
It has a name, but we still have some communicable language for it. I agree it's not as much. And the other thing I think is that if I stop, we started working on loading a dishwasher, right? And now I watch myself while loading a dishwasher and it's fascinating. And there's all this stuff that I never paid attention to before. And what we're doing is pretty subtle. And it was all kind of in the noise before. That was just not in my cone of attention. So maybe it's just lower in the hindbrain or something. I don't know exactly what that is. I agree with you that we don't speak about it as well. We don't communicate it as well. And maybe that hinders our research. I don't know.
Okay, but you don't think it's the task domain itself? Like it's not something intrinsically non-parsable about geometry, which would be kind of horrible.
Maybe we haven't discovered the right representations yet. It's a good question. I think Newton and Galileo and these guys did something pretty magical when they started summarizing pretty complicated things with pretty simple equations. That's not what we're trying to do with the deep networks. So maybe we should. Somehow we've gone from there. We've gone everything more detailed, and I think we're not going to the here's a way to talk with simple equations about really complex things. But probably I have to think there's some other Newton waiting around the corner.
Yeah, I guess we'll have just one last question from Swami. By the way, both Greg and Russ will rejoin us in the panel discussion later today. I'm sure Greg has reserved a bunch of even tougher and more exciting questions for the panelists. So last one.
Sorry, Quan, I have to interject. I'm counting on the audience to come up with tough questions. So if you're there listening, you have to think of the questions to have them ready for the panel.
So you hear, Greg? Okay, well, let's see what's going to happen in the afternoon. And last question from Swami. How do we ensure that the items in the plate doesn't fall while grasping? Is there any approach to train safety critical, I guess, probably risk sensitive key points?
Okay, cool. So the specific answer to that specific video I showed was it completely ignored the orange and the napkin and everything like that. It was designed to just be immune to that. So it was not trying to keep anything on the plate or not. The question of risk sensitivity is obviously one of the biggest ones we face right now for some applications. And even though I think you're not as likely, manipulation doesn't feel as safety critical as driving or something else, but I still think, I'm not going to sell anybody a home robot if it breaks dishes like twice a day, right? So I think robustness is a serious topic. I worry that imitation learning straight into a deep network isn't a path to having any confidence that I think we need to have. But I think it's a starting point. It showed us a representation that that can work, can achieve a level of performance. And now I think our job is to sort of learn from that and extract the parts, and maybe we can fit it in a few set of simple equations that we could verify, we could reason about, at least understand when it's out of scope.
That's a great answer. Let's thank Russ again, and we'll see you back at 4 p.m. Yeah, Pacific time. See you guys. That concludes the morning session of this workshop today.